Okay, so we can skip the derivation part because I also do not have at the moment. If you really want, then I can refer some textbook and in next lecture we can discuss it.
Sir, please discuss question 10 of assignment.
Which assignment?
Assignment 3, MOSFET 1.
Assignment 3 MOSFET. Okay. So let me see the problem. Yeah. Just a second. This is really a good question that has been framed. So let me bring the question on the screen. This is the question, right? Yeah. So in this question,
We are
you know,
seeing the web actually.
sorry.
We are seeing the screen, the Chrome actually.
Okay, you are seeing the Chrome.
Yeah.
Okay, you are not seeing the whiteboard.
No, no, no.
Okay, sorry
I
for that.
At least I'm not. I mean, yeah.
Yes, thanks. Thanks for letting me know. So this is the problem you are talking about, right? Could you please confirm it? This is the problem you are referring to?
Yes, sir.
Okay, thanks. So here, you have a gate to source MOS capacitance. Basically, let me draw it. So there will be some parasitic capacitances always present between your gate to source, gate to drain also. But here they have mentioned that it is connected to gate to source and its value is given. So basically, from the given information, you can extract uh, your gate to source voltage is given, that is there 12 volt, and your source gate to source capacitance is also given. So I think you will be able to calculate your charge present between that capacitance, right? And now that gate current required to sustain the turn on of MOSFET. So that conduction period, that is somehow all, let me write it. Q is equal to CGS, QCGS equal to dV by dt. Okay. So for finite value, you can put here dV is equal to 12 and dt you can take the period that is it is asking to sustain the turn on. So that much time, either you can refer any data set also. So you take that time and you will be able to calculate that value of current. So you can easily get the value of charge. After that, you just need to multiply or divide it with capacitance and voltage. So you will get current. Sorry, this will be I, yes, CGS into V. VGS. So from this expression, you can calculate the charge present between gate and source, and after that, you can dq by dt. You can apply, and you may put the time for turn on, and you have anyway this charge value, so you can go ahead with that.
Basically, we can refer any MOSFET data sheet.
Sorry, can you
Uh,
repeat?
the turn on time, we need to see some reference data
Yeah.
sheet.
Yes.
Any
Yes. That I cannot tell where from where you can look, because
But
I
what I'm saying is it may vary, right? I mean, it can vary.
yeah, it may vary. There you have to put your brain, like what
Okay.
will be the value of dt, right?
Hmm.
Since in the problem it is stated that this much gate current required to sustain the turn on, so you have to find out, you have to puzzle it out, that which value should you take in account for turn on period.
Yeah.
Yeah. Okay, so
But no specific MOSFET detail is given. Then how to get the time from a data sheet?
uh, if if it is not given in data sheet, then you can take any unit charge or something, unit time or something like that. You can. That's what your question, right? If it is not given in data set, then how will you find out?
Yes, sir. But actually, this problem is not a numerical problem. It's a logical question.
Yeah.
Yesterday itself, the answer was given.
Okay. In yesterday's
Itself,
session.
live session, the answer was given. It
Okay.
was not a numerical problem where you don't need any formula and all. They have asked for to sustain the turn on.
Hmm.
So already gate source voltage is 12 volt means already the MOSFET is on. So you don't require any gate to sustain the turn on or to maintain the current. So the gate current required is 0 amps. That was the solution given yesterday.
Okay. The solution was given yesterday. So that's
Yes, yes, yes.
okay. Then you can go ahead with that. No issue, I guess. Right. Otherwise, I just told what are the methods you can prefer. It might be logical, it might not, since answer is not out yet, so you can think of that. Anyway, so we will move ahead with some problems of previous year questions, assignment problems.
Can we also discuss on question number 5 first?
Question number 5. Yeah, definitely. So this is the problem here. You need to find out the percentage difference in current sharing if current sharing series resistances are this and this. Okay. So two MOSFETs are connected in parallel, of course, to share the load, and the current which is coming from the supply, that is 20 ampere. VDS1 is given, VDS2 is given. You have to determine the percentage difference in current sharing. So yeah, this is the typical parallel connection circuit. If you have solved any parallel connection circuits, like parallel connection of alternators kind of thing, so you just have to equate the voltage along this two terminals. Then from these two voltages, you will get two different equations, right? From first, if you apply KVL from this node to this node 1 to node 2 in first part, right?
Yep.
And in second part also you can apply. And here you have to compute in terms of id1 and id2 will be in terms of id, like vds1, this drop, you just need to compute this id rs1 and id2 rs2, and then you have to equate both equations and you will get one ratio based on that.
So difference in percentage difference in current sharing would mean if we get a ratio.
Yeah,
So basically the difference
yeah, go ahead, please.
percentage difference in the current sharing.
Uh-huh.
So basically,
So if you get the ratio, you can calculate the percentage, right?
yeah. So difference of that percentage you need to put.
Yes, that you need to put in the answer box.
Mhm.
So, okay, so we will move ahead with some problems, then you will get some clarity, and in last also we can anytime discuss these assignment, current assignment problems. So let me take one MOSFET based problem first, then you might gain some insight. So this is the problem here. An N-channel MOSFET is given in this figure. Threshold voltage is given 2 volt. ID current is also given 4 milliampere. Okay. This VTH is 2 volt. ID current is given 4 milliampere. And when drain resistance is 1 kilo ohm, this RD is 1 kilo ohm. And now we have to find ID in case of RD become RD2 become 4 kilo ohm. So that ID2, in that case we will assume drain current would be ID2. So that you have to find out. So we will move ahead with some basic equations. First, since we have to focus on drain current, so that drain current is equal to K VGS minus VGS TH all square, right? And after that, and we can see from this circuit here, this gate is sorted with your drain terminal. So VG will be equal to VD. And so if we calculate this VG, then we will be able to calculate VD, and after that we can find out the value of K, since we know VGS, sorry, we know VGS of threshold value, right? And we know this current, and we know this 10 voltage supply, so we will move a step by step and we will try to find the value of K from this equation. So here we will take first case first. I hope you must have read the problem. Let me keep it open for just some time. So you just read this problem once. Everything is given. What you need to compute and what are the conditions when we need to compute drain current when resistance is increased from one value to another value. So for that purpose, we need to know the value of K, since ID is proportional of that K. So if somehow we find K, then we will be able to find other things. What will be the VG or VD will be for second case, so that we will find. So for case one, ID was 4 milliampere. So we can apply this KVL between this node. So 10 minus RD will be this VD. So VD will be 10 minus RD, and ID was 1 milliohm, sorry, 1 milliampere. 4 milliampere and drain resistance was 1 kilo. 4 milliampere, this is 1 kilo ohm. So VD would come out to be 6 volt. And it is sorted with VG, so the same value will be there. So VD is equal to VG, we can say for the first case, and source is anyway, it is connected to ground. So VGS is equal to VG minus VS, and your VS is connected to ground, so it will be 0. And after that, VGS will become equal to VG, and it will be 6 volt. So in first expression here, ID was given, VGS TH was given, VGS we did not know, so that's why we computed VGS, and now we can easily know the value of K from this expression. So that's what I will do here. So K will be ID divided by VGS minus VGS TH square. So it will come out to be 4 milliampere. VGS is 6 volt and VGS TH is 2 volt square. So it will be 1 by 4 into 10 raised to power minus 3 ampere per volt square. So this is the value of K. It will be fixed throughout the operating point. Means for any particular operating point, this K will be fixed. Okay. So if you now have changed the resistance, so for that changed resistance, we need to compute ID, and this K value will be fixed. And if somehow we can compute the VGS for the next case, so that would be the final thing to get the answer.
Excuse me, sir.
Yeah, go ahead, please.
Sir, in above, you have taken VD equal to VG. Please explain it.
Okay, yeah, sure. Yeah. So from the circuit, are you able to see that your gate terminal is sorted to drain terminal?
Yes, sir.
So that potential, if the wire is sorted, so potential will be same throughout, right?
Okay, sir. Sorry.
Purnima, I think you might be able to see the question now. Question 5, shall we use current division rule? Question 5. Okay, I will come to question 5 in a while. Okay. So let me complete this problem first. Then we can discuss again the question 5. So we computed the value of K. Now for case 2. RD has become 4 kilo ampere. Sorry, 4 kilo ohm. And now we need to compute ID for this value of resistance, drain resistance. Now our VD will not be same that we computed 6 volt, because this current will change and this drop across this RD will change, and that will change the value of VD. So that value we need to compute. So this VD is equal to now 10 minus 4 ID, right? and this ID will be K into VGS minus VGS square. The equation is same. Now VG was anyhow or for the given circuit it is VD, and Vs is grounded, so it will be 0. So now VGS, we can write it as VDS. Okay, I hope no doubt in this point. That is true for this particular circuit. That is not true always. And VDS, why I am writing VDS? Because we need to put two equations in one format. So if we have two equations and two unknown, then we can easily find out the value of this ID. We are trying to find out this value of ID here. So let me write it. ID is equal to K we computed, that was 1 by 4 into 10 raised to power minus 3. VGS will be equal to VDS equal to VD. Okay, and VD we can write 10 minus 4 ID. So now you might have guessed correctly that it is going to be a quadratic equation, and VG is threshold value is 2 anyway. So this is your expression. One equation and one unknown, and this will be your quadratic equation 4ID. Sorry, it is equal to 4ID.
This is for square, no? It is square and it is not for 10 minus 4 ID. This is for 10 minus 4 ID minus 2 the whole square, no? Expression.
Yeah, you are correct. You are correct.
Yes, remove
Sorry
that.
for the mistake. Here you can square it. Yeah. So 4000 ID will go to the left side, and this will become 8 minus 4 ID square. So if you solve this quadratic equation, or first if you arrange 16 ID square minus 32 ID plus 64 is equal to 4000 ID.
Minus 64 ID. 2A. Minus 64 ID.
Okay, yeah, uh, that is minus 64 ID. Yeah, you are correct. So in ID square minus 1000 6 minus 966 ID 64 is equal to 0, and if you solve this quadratic equation, you will get the two value of this current. Let me tell you the values. So 2.843 milliampere, and another will be 1.407 milliampere. So two values you will get, and both are positive. So now the question is which value you should consider. So any idea about that? Yeah, so yeah, I will share the sheet after this. So any idea about which ID we should take and move on? Yeah, Santi, you are trying to say something. Okay, so clearly from these two values, we cannot conclude anything. So we have to move one more step further, and now we need to identify VGS, right? Since we obtained the value of ID, we can compute VGS, and we will see if any sensible value of VGS is coming from any one particular value of ID or from both ID. So that we will have to see, and we will reach to some conclusion after that, I hope. So VGS is nothing but VDS is nothing but VD. I am writing this equation based on the given circuit that is sorted, gate is sorted with your drain. So let me bring back the circuit. So VD is equal to VG and S is 0. So VDS is equal to VGS. So from this circuit, I am writing all that equation. Yeah, so this VD was equal to supply voltage, that is VDD, minus your, this time our resistance is 4 kilo ohm, 4 kilo ohm into ID, right? This is not constant here, let me remove it. So whatever ID will come now, that will be in milliampere. So VDD was 10, VDD was 10, and if we put 4 into ID, the first value of ID, that is 2.843, so you will get by this calculation minus 1.372 volt. Right? Any doubt? Someone is trying to speak something. Okay. Anyway, so we will move ahead. So with this value, you got the negative value of VGS for N-channel MOSFET. And what do you have comment for this value? Can you accept it or should you discard it?
For N channel, negative gate voltage cannot be taken for N channel
Yeah,
MOSFET.
perfect.
So
You are
this is
correct.
ignored.
Yeah, so it is going to be ignored because VGS will be negative, then our MOSFET will not form
Not
any
conduct.
channel and it will not conduct. Yeah, you are correct. So just for the sake of verification, we will take another value and we will find out what is the value of VGS. So 10 minus 4 into 1.407, and it is going to come out to be 4.372 volt. So yeah, this VGS is higher than our threshold also, and it is greater than 0. So it will allow to form the channel, and this value of current is perfect, means it is perfectly correct to have this kind of drain current so that our gate can form channel and it will conduct. So we will finally consider this as the answer for the problem 1.407 milliampere. So any doubt in this problem again? At any point, any doubt you felt?
This VGS equal to VDS minus VS, but VS is 0. That's why we equated, right? VGS is.
Yeah, you are correct. Since source is grounded, so VDS or VGS is anyway going to VD or VD. So anyway, you think about that, and let me present Mhm. Related to your question that was discussed in the starting, uh,
This textbook is available.
no, you have to purchase it. It is not available, and you may search somewhere. Actually, I got this based on um, whole page. Like I had some, I this book was with our colleagues, so I took that. You may also look with your colleagues, and you can find it out. Or anyway, you can search on Google that what happens, why we do not connect any other things apart from Zener diode also, or what will happen if you leave it as it is, or what will happen if you touch the circuit. So that those things are there. Okay, so yeah, it is better. It is always better to read the reference books by the course instructor who is teaching the course, so that you will get the insight on what he or she is trying to convey the topic in which way. That's why I just wanted to show that. So okay, so let us move ahead with some another problem. So I hope this problem would be fine here. Okay. Yeah, so this next problem is based on the losses. So what will be the losses in MOSFET, and how will you compute the losses in MOSFET, conduction losses, and of course switching losses would be similar to all. It will be true for all the switches, whether it is a diode or BJT or MOSFET or any other switch, because any switch will switch. The switching thing will happen in similar fashion, that just that the rise time, fall time, delay time, this kind of things will change. Otherwise, it will be same for all. And generally, it will be triangular falling and triangular rising. So most of the time, not always, it will come in the format of Vi by 6 into T into F. So this is more general if you do not want to spend much time in exam and you see the waveform of current is falling like that, current is falling like that, and voltage is rising like that for the same period, you just close your eyes and write Vi by C, and whatever this time is there, whether it is given in terms of duty cycle or something, you write it and multiply it with switching frequency, and you would be good to go. Otherwise, no duty ratio you need to consider. It will be simply Vi by 6. So this is most popular formula for switching losses. If you derive, just like in last session, I derived the slope of current and voltage and integrate, and then you will multiply it with what frequency, you will get the same thing. So I hope you might have solved in the last assignment. For assignment 2, for BJT, there one problem was given like that. You just verify these things, you will get the same thing. So moving ahead, in this problem, we are asked to find out the average on loss state. So this MOSFET is rated for 15 ampere, okay, and we do not need to compute switching losses. We just need to compute on state loss, so conduction loss basically. Let me erase it. So you all know, you might have referred that lecture where professor derived that, not derived, he might have told, let me bring the dynamic characteristics slide off. So you may see the slide of dynamic characteristics if you have gone through the lecture. And here, when the switch is on, it will have a particular resistance that will be RDS on, and it will be multiplied with ID. And anyway, you know that during conduction, your VDS will be very low, otherwise the losses will be high. And MOSFET in itself, it is a high frequency device. So if VDS would be higher, then it will cost you in terms of losses. And in the problem, we are not given with the value of VDS, but we are given with the value of RDS, right? And MOSFET is generally modeled as a resistor because of the reason VDS is ID into RDS on, because this parameter you will easily find in the data sheet, and it is a majority carrier device for your information, and it can be modeled with RDS. So why it is modeled as the RDS and why not other switches are modeled as a resistance? So do you have any idea about that? Anyone? I think I have given a hint here, but can you take live meeting Zoom for next time on? Uh, Sorry, Anaga, I cannot do it because we are not allowed to take that, because this interface is common for everyone and we have already given all the information. So I'm sorry, now I cannot change that mode of these sessions. Please let me know if you have any issue with Google Meet. We will sort it out. So yeah, so I was on the problem that why it is modeled as a register basically. Can you think in terms of majority carrier device? It might have some relation with majority carrier device. Uh, okay, so let me bring back one figure. This is the common operation of MOSFET. Let me write two, three things. Is this MOSFET voltage controlled or current controlled?
Voltage control device.
Voltage
Voltage
control.
control.
Yeah, that is right. Thanks. Why voltage control device? Because you are applying your voltage to create an electric field, right? It is not conducting directly. No any current is flowing like that, as you might have seen in BJT or IGBTs. So there one conduction channel is there. But here what is happening? This electric field is creating in such a manner so that P layer is getting depleted and N channel is flowing in this flow, right? There will be one channel this electric field will repel the holes or whatever positive charge carriers, and it will create an n channel. And that once n channel is created, it will allow all the electrons from drain to source, sorry, source to drain. It will allow all the charges to flow, right? The charges will flow from source to drain, and then current will flow from drain to source. Means both are same statements. If electrons are flowing from source to drain, if electrons are flowing from this direction, then how we write the flow of current? The flow of current will be right to left. So that's what here happening. Your charges are flowing from source to drain, and your current is flowing from drain to source. And it is being controlled by the voltage whatever you are applying. Once this applied voltage surpasses the threshold limit, that is VGS-TH. Every devices has their own different threshold value. So when that value is surpassed, it means channel is cleared. Sorry, channel is created, and it has been depleted by the amount that is required to conduct the flow of current, and now you can flow. So that's why this kind of characteristics you see, right? Mm. So till this point, you apply VGS, no current will flow, and after this VGS TH value, your channel will be formed here, and it will increase a square of your this VGS minus VTH. It will be directly proportional to VGS minus VGS TH all square. So when the channel is formed, so no much effort will be required and it will flow smoothly. Right? So that is why it is called voltage controlled and majority carrier devices, because for n channel MOSFET, the current is flowing due to only n type of carriers, like they are majority carriers, and this minority carrier will have in source, right? The source is connected to your minority, this minority block, that P block. Here source will be connected, and that will be depleted, and your majority carrier devices will start to flow. So that's why it is a voltage control device and majority carrier device. So again, coming back to the question, my question was, why do we model it with resistance, right? Uh, be- because of this majority carrier conduction, you increase the temperature. What we will observe, that this device will be positive temperature coefficient device, right? Generally, BJT and IGBTs are which coefficient? Like if we increase the temperature, what will happen in BJT and IGBT? Its resistance will increase or decrease. I'm putting a question here. If you increase temperature for transistors like BJT or IGBT, uh, yeah, so what will happen to the resistance of the device?
Collector emitter terminal will
Negative temperature coefficient.
Negative temperature coefficient. Yeah, correct. That's what I was asking. So your resistance will decrease, and that's why that thermal runaway kind of things happen in BJT or IGBT. Once you are conducting your switch for any application. Let's say you are connected to an inverter. You have connected this BJTs and IGBTs to any inverter or any rectifier. Now what happens? Current will flow. Current will flow. Some losses will occur. That losses will increase the temperature. Okay. When the temperature will be increased, your resistance will be decreased because this is a negative temperature coefficient. Some of you correctly pointed out. So, when temperature increases, resistance decreases. Now, is it good or bad?
Once again current increase, once again temperature increase.
Definitely. So, here resistance will decrease, current will further increase, temperature will increase, and it is a cumulative process. Your temperature will increase, and at a certain point, your transistor will be damaged. So that's the drawback, and that's why we do not connect BJTs in parallel connection, because with parallel connection also these kind of drawbacks are there. In one BJT, if higher current is flowing, in another BJT lower current will flow, and the BJT which was carrying higher current, the current will gonna increase, and your temperature will increase. So that was the drawback of minority carrier devices. So and they were minority carrier devices. Yeah. So in MOSFET, those kind of issues we have compensated here, and now here it will operate as a positive temperature coefficient. Okay. Because of the reason it is a majority carrier device. So with positive temperature coefficient, your temperature will
So
increase.
minority carrier devices are positive temperature, sorry, negative temperature coefficient devices.
Yes, yes. That's what I am trying to conclude it here. Yeah, you have any doubt in that?
BJT is we have both minority as well as majority charges. How can we say that it is?
See, definitely that majority charges flow, but what are in dominate? Which charge carriers dominate there?
Sir, then why it is used in inverter?
So,
IGBTs.
sorry.
IGBTs, why it is used in inverters?
Yeah, because there are regions we do not always use IGBTs. IGBTs have several advantages, and first advantage is it can withstand very high voltage level and current level. So if you are operating high power level devices, then will have to go for IGBTs. And IGBTs have another things, because IGBTs comes in between MOSFET and BJT. So that thermal runaway will not be severe in IGBT if you further discrete between IGBT and BJT. So uh, let me write it: BJT, IGBT, and MOSFET. Right. BJT is simply a transistor. So here is no support of any other devices, right? But IGBT has a diode connected in series inherently. So because of this diode, uh, let me bring back that slide so that you can visualize that better. Yeah. Are you able to recall this slide? If you have referred the lectures, then you might be able to recall this slide. So you see here a PN junction is a formation of PN junction, extra PN junction is happening there, and because of that, You know, this MOSFET will block the positive voltage and this diode will block the negative voltage. These are the common things which you can identify from any switch. So because of this another PN junction, that thermal runaway will not occur to the extent what was occurring in case of BJT, because BJT will not have any support of that, right? So these junctions, this extra N layer, you are having an extra N layer, that layer will support its flow of current. So that helps in withstanding higher voltage level and higher current level. So IGBT is most rugged device, and definitely where you can do your work with a bit lower frequency, where you do not need very high pulse frequency such that a PWM inverter or something. You can safely use IGBTs. IGBTs are most preferable device. BJT, not much people use nowadays. Either they use IGBT or wherever high frequency is required, MOSFET will be there. So the thermal runaway will happen large in BJT, after that IGBT. If you want to further discrete it, and then you can write MOSFET if you are arranging between these devices. In MOSFET, it will be negligible, but that's how it works. So that was the reason I
So,
stated it. Yeah,
what was the answer you gave for BHD is both minority and majority charge carriers? Then
yeah,
how?
I agree to that. I agree to that. That
Okay.
is true, but that current is a leakage current, and that is very small current. That ICEO, you might have solved that loss problem. Was in assignment 2. Did you find out the difference between loss during off state and loss during on state? So
I didn't remember. It was there, but I didn't remember the value.
okay, so I also do not remember, but there was large difference between them. So your majority carrier flow will be there, definitely it will be there, but it will be such a small that you have to ignore that. Right? If it would have been in like of any other like IGBT or something or MOSFET, then you can consider, but for such a small value, you cannot consider that it is a majority carrier device. So that's what I am trying to convey here.
Okay.
Yeah,
By
just
saying the seeing the value, the problem, we found that the IC naught is has a predominant value.
yeah. Switching losses were the dominant. After that, conduction loss and this off-state loss was very small.
Oh,
Yeah.
okay.
Okay. So please excuse me for a minute. I will be back just in 1 minute. Yeah. So I'm back here. So that's what we discussed, that MOSFET can be modeled as a register. So the overall conclusion is MOSFET can be modeled as a register, and why we can model it, we just discussed that. So we should go ahead with the problem here. So rated current is given in the problem, and that is 15 ampere, and on state resistance is also given. So if it is a resistor, power loss would be IRMS square into RDS. And sorry, I forgot to give the graph of current so that you can compute the value of RMS current, that I will bring back. So this is your current waveform. From this waveform, I think you can easily compute the RMS value. Its peak value is 10 ampere and it is conducting for half the cycle. So its ID RMS would be 10 by root 2. Should I explain this thing? How it is coming 10 by root 2? Generally,
Not required.
sorry, I did not get it.
This you have told in the previous class itself.
Or in converters, DC to DC converters, you will
Incorrect.
see this kind of waveforms quite frequently. So basically, the thing is, if you have any square waveform, you write first the peak value and under root for time it is conducting and total time
I
period.
see.
So T on you can write it as further if you go ahead. T on will be equal to dt. D is duty cycle or duty ratio, sorry, and T is anyway T. So finally, it will come out to be
10 root
T. Yeah, correct. And D from graph you can see it is conducting for half of the period pi by 2 pi. Is your D that will be half.
2.5.
It will be 10 by 2 ampere. That is RMS value. And coming back to the loss, this 10 by root 2 square into RDS was 0.15 ohm. So you will get 100 by 2 into 15 by 2, that will be 7.5 watt of the conduction loss. So this will be your answer for this conduction loss. Any doubt once again in this problem? Yeah, so I hope it was pretty straightforward problem. Just you need to find out the RMS current and after that it will be.
Sir, is IGBT is having negative temperature coefficients?
Sorry?
Uh, what about the resistance for IGBT, sir? Coefficient of resistance for IGBT?
Yeah, we do not model IGBT as a resistance, do we?
No.
No. So we do not model it as a resistance. That's what the reason behind discussing all the majority and minority carrier devices. So MOSFET generally, it is very general. It can be varied case to case, but generally MOSFET is modeled because of as a resistor because of the reason majority carrier device it is considered, and IGBTs and BJTs are considered as a negative coefficient device. So there you have to model it appropriately. Did that answer your question or anything
Yes, sir.
else?
Yes, sir. Yes, sir. It's fine.
Yeah, thanks. Let me bring one another problem. So this is the problem here. We need to find the voltage between A and B terminal. So here we need to find the voltage, and in this circuit one MOSFET is introduced, and because of the MOSFET what effect will be there that we need to think about. So its threshold voltage is also given 1 volt. So any idea which approach should we take? Okay, so we need to find out the voltage between A and B, and when this switch will be on, then we can model this MOSFET with what?
Resistance.
Yeah, of resistance. RDS. So the thing is, now we will draw the equivalent circuit again. 10 volt. So, do you have any comment on this 8 volt source? Could it come in picture of this circuit, or could we avoid it? What will happen to 8 volt when we model the MOSFET as an RDS?
There's no need to consider VGS here.
Yeah, you are correct. So no need to consider this 8 volt. We can easily eliminate it because anyway it is isolated to our DS, the terminal D and S. So it is isolated, right? It is just there to create channel. So we can ignore this 8 volt. Now this is your circuit. But again, if you read the problem, that there is no information regarding RDS is given. Okay. So if any RDS would have been given, then you could have easily computed based on KCL, KVL, you would apply one nodal equation, you would get your value. But here nothing is given, and one important word is written, that is ideal. So in ideal case, RDS value we can safely assume equal to 0, and after the assumption of RDS is equal to 0, this circuit will be replaced with a short circuit wire, and once this wire gets sorted, the voltage across here will be 0, right? And if voltage across these both terminals x y, let us consider, is 0, so anyway this 0 would be reflected to your output because no current will flow in this direction. If this circuit is short circuited, I will be 0, so all the current will flow in this manner. And if no voltage, if no current is going in this direction or this direction, so all voltage drop is 0. So here 0 into 2 kilo ohm is 0. So your answer would be 0. Any question? And drain voltage. Okay, so I can safely assume that no question on this. Yeah, so in the meanwhile, any doubt in current assignment, just doubt, not complete solution I can discuss, but any doubt if it is there that we can refer. You do not have any issue with heat sink kind of problems or temperature distribution.
So can you discuss third question, so which is related to junction temperature?
Junction temperature, yeah. So this third question is related to second question. In second question, we had to calculate the power loss, total power loss in the MOSFET. The particular MOSFET is given, and you need to compute total power loss, conduction loss, and switching losses. And after that, you will get some power from question number 2, power loss. Calculate from question 2. I hope this should not be any issue. And once you compute power loss, so what happens? For losses, for the design of heatsink, we generally consider power as a current, flow of power, because these power losses are nothing but the dissipation of heat, and heat is flowing, right? Just the charge and like the charge and current. So this power loss is generally modeled as current, and it will always flow from higher temperature to lower temperature. So these temperatures are modeled as resistors, and your thermal resistances, sorry, this thermal, sorry, this temperatures are modeled as a voltage, because these temperatures are the temperature at any 2 points from higher temperature to lower temperature it is flowing. Let's assume T1 to T2, and this thermal resistance is connected. So this thermal resistance is written as theta, which is similar to what we see resistance in our circuit. So this temperatures are similar to our voltage, and this theta is in degree centigrade per watt. So we generally go from inside to out. So the innermost temperature node is junction. After that, sink, junction to sink. After that, we go sink to case. Sorry, no, junction to case, case to sink, and sink to ambient. So in this problem, we need to find out the thermal resistance between case to ambient, right? So you have given the temperatures of junction, ambient. So Tj minus Ta you are given, Tj and Ta you are given. What should be the maximum value of junction to case thermal resistance? So that you need to find out, and based on that value, the thermal resistance value, what you will compute from the given power loss, that you will compute from the problem. Based on that, you can choose the heat sinks from the market, and in this problem, that value of case to ambient thermal resistance you need to compute. You have the value of power, you have the value of junction temperatures, just you need to apply the this thermal Ohm's law, you can say informally, and you will be able to get the value of case to ambient thermal resistance. So, any doubt in this? Okay, so I hope it is clear.
Sir, fourth question.
Sorry,
This answered fourth question, sir.
sorry, I'm not getting you.
Fourth question. I'm hearing.
Fourth question. Okay. Yeah, fourth question is,
Yes, sir. Computing the current expression
yeah,
K into VT minus VT.
VGS whole square. The drain to source voltage is given. Yeah, so I think this is really a straightforward problem.
Yes, the concentration what we said previously, no. K
Yeah,
into VGS minus
VGS minus
VT.
VTH, and both
Okay.
both values are given. So
Given.
yeah,
Taking ratio we can find.
yeah, K will anyhow get cancelled out. So you can easily find out the.
Okay.
So let me take some problems from thyristors as well. Huh. So we will see one problem from thyristor. Thyristor latching current. Do you know what is the latching current for a thyristor? Yeah, could you please speak louder? I have today some issue with my earplug, so please.
Minimum anode cathode parameter so that it can turn on.
Uh, I'm really sorry, I could not get you. Anyone is getting him? What he is trying to say?
Voice is low, sir. It's not audible. What he's talking.
You are not audible properly. Okay, anyway, so the latching current is it is given in the problem itself. It is the minimum current that should flow through the thyristor to turn it on. Okay, there are two terms: latching current and holding current. Okay, so holding current is the current that will appear during off state when we are going to turn off the thyristor. Okay, we have to force the charge we saw. We have to force the charge in that manner so that the holding current would be surpassed. So this holding current is the level below this value. Thyristor gets off. Okay, and latching current is the value when thyristor will be turned on. Right. So both are two different terms, and we use them during turn on and turn off for two different conditions. So in this problem, we need to find out the minimum width of gate pulse that is required to turn on this thyristor, right? This thyristor is connected with an inductor and latching current is given.
Sir,
Yeah, go ahead, please.
these devices, thyristors are being used in industries as like MOSFET and IGBTs.
Uh, See, thyristors are getting used, but not in inverters, most popular inverters. If you take example for traction application, now these days we are seeing electric vehicles and all.
Yes.
There we avoid thyristors because to turn off the thyristor it is a quite tedious process.
Yes.
But in large motor industrial applications where to generate the electricity, where we use high powers like 2 megawatt or 3 megawatt in the level of megawatts, in that level of power, at that level of power, your thyristors become handy because thyristor is very rugged device, and this thyristors has very high capability of voltage blocking and current conduct current conduction capability. And also, if somehow you can do the load commutation of thyristor, so what happens if you do load commutation, then you would get rid of any external commutation circuits. In further lectures, I hope you will see the commutation circuits for these thyristors, so that you do not have to apply there. And this kind of commutation circuits can be eliminated with the help of load commutated. And load commutated circuit, when they will come in the picture, when your load will be operate at leading power factor. So that is again contradictory kind of thing. If any motor or any machine is having leading power factor, then they will supply reactive power back to us. So I I think most of the motors work on lagging power factor. That's why thyristors are avoided in traction applications, or say any other applications which generally operates with battery and all. So there we do not prefer thyristors. So there we go for MOSFETs or IGBTs. So does that answer your question?
Yeah, yes, sir. Only MOSFET and IGBTs are predominantly used in all places.
Yeah, you are correct. And nowadays research are also going with some another high speed, high frequency devices like silicon carbide and gallium nitride. You may hear in future. Some at some places it is being used, and for these kind of devices to become more general, more R&D efforts are required in that direction. So you may see in 4 5 years that some electric vehicles are commercially using these high frequency devices. Their
Okay.
frequencies are much higher than MOSFETs. So you may see in future.
Okay, sir. Thank you.
Yeah, thanks. So in this problem, we need to compute the minimum width of gate pulse. Okay, to turn on the thyristor. So from these conditions, we are sure that minimum current must flow in the circuit. How much? 4 milliampere. That is latching current. If minimum this much current will flow through the circuit, your thyristor will be turned on. And to flow this kind of current, and for how much of width, generally we deal in terms of pulses, right, in power electronic circuit. So how much the width of this kind of pulses we should consider, that we have to think. So you know this
Sir, we have
pulse,
to,
sorry.
sir, in this question, we have to give the pulse to the time where this current ramp up to 4 amps.
Yeah, we need to compute that width
Time.
on in terms of time. Yeah, in terms of time. You are correct. In terms of time, we need to compute how much time we will give this much for milliampere current, so that our this thyristor will be turned on. It will not like that you just provided 4 milliampere and it will be turned on. You have to give it for some finite duration. So that much duration you need to compute. So this minimum width of gate pulse in terms of second. In the questions, in this question, it should have been mentioned that in terms of second, right? In time.
Yes.
Is it okay, Muthu
Yes, sir.
Kumar Swami? Yeah.
Yes,
Thanks.
yes.
So this T latch we need to find out. So which expression we will apply here? Initially the thyristor is off. Now we are providing current of latching current. So current is getting changed from 0 to 4 milliampere. So can you recall any expression or any relation between inductor voltage and current?
Yes, LDI by dt.
Okay, perfect. So V is equal to L di by dt. L is given, that is zero point 0.1 Henry. So del I by del T, I am considering T latch equal to del T and equal to V by L, and V by L is 100 by zero point 0.1, that is 1000. So del I by del T is equal to 1000, and del T would be T latch, and del I would be 4 minus 0. So 4 minus 0 divided by T latch equal to 1000. Now if you further do simplification, you will get T latch is equal to 4 by 1000. So 4 millisecond. So the value of 4 milliampere you need to provide for at least 4 millisecond to get this thyristor on, right? So that was the problem based on that. And once you turn it on, you cannot turn it off, right? Because it is not a fully controlled device. It is semi-controlled device, this thyristor. You have control on, turn off, but once it gets turned on, then you cannot turn it off. Then you have to apply some commutation circuit, or you have to provide some load, so such that load would provide inherent commutation. So that's the thing that we have to deal with thyristor. Thyristor is really a great device, but the issue is with you do not have control on turn off. I hope this problem would be fine. Let me see. I can take another problem. So, you know the difference between controlled, fully controlled, semi-controlled, or uncontrolled device, right? I just want to recall it. So, is IGBT is which kind of device? You just need to tell in terms of fully, semi, or uncontrolled.
Fully controlled.
Correct. So, IGBT is a fully controlled device. What about DIAC?
Uncontrolled device.
Yeah, it is an uncontrolled device. SCR, just now I told that it is semi-controlled device, and the other diode is an uncontrolled device. Mm, okay, so these are some things. Okay, so should we discuss one more problem based on this latching current and thyristor? So now this say the circuit here. Again, the same thing you need to find out minimum pulse width, and but here it will be a bit demanding question because you need to recall your transient concept, right? How this RL circuit works. So that you need to find out. So again, the latching current is 50 ampere, milliampere. Minimum pulse width you need to find out. So that we will go through. So, so here the time will come from your inductor RL circuit transient concept, and since it is it is connected to source, so basically your inductor is getting charged, and that charge current, its expression is explained in terms of I note. Let me write it here.
Sir, in this problem, can we solve by removing the thyristor?
By sorry.
By removing the thyristor,
Ha, ha, ha.
can we solve and arrive and find the time at which the total current reaches 50 milliamps?
Yeah, that's what we have to do. That's what we have to do. But how much current is flowing, that will also be dependent of time, right? That will not be time independent.
Yes.
So this current, this let us say IL would be how much? That whatever current is initial 1 minus e raised to power minus t by tau, where tau is equal to L by R. If you recall the concept of your transient, right?
Yeah, DC branches.
Huh. So if 50 milliampere current is needed here, that current you can write it, you can apply IL, but latching is also, we will distinguish it with I latch. I latch is equal to IL plus IR, right? So, and IR, how to find IR? Because IL we derived an expression I naught into 1 minus e raised to power t by tau, right? And two parameters that are unknown till now, I naught and IR. Could you please try to hint me how to compute IR and IL?
There is just 100 by 5K
Yeah,
IR.
perfect. IR would be 100 by 5K. What about I naught?
I notice this initial value of current is 0.
How so?
It is given in the question, right?
It
I
is
think
given in the
it is not visible.
Okay, okay. Let me zoom it for you. Now, is it visible?
Yes.
Okay. So please read the question once.
When the thyristor starts conducting,
Huh.
we can say that inductor will be having a short now.
Yeah,
So,
that we have to assume that thyristor has been latched and current is flowing 50 milliampere. And
steady state.
yeah, we will sort that thyristor. Definitely, we will do that.
In that case, 100 by 20 ohm.
100 by 20 ohm, definitely. That would be your initial current, because please try to recall your transient concepts, what used to happen.
That is a
So,
final current.
Yes, that's the final current.
yeah, that's the final current. Did I say initial current?
Yeah, you said as initial current.
Oh, okay, sorry, my bad. It will be final current. Okay, so that will be final current, because we are going to compute that current when your thyristor has been latched. So obviously it will be final current. So IL would be, sorry, I naught would be 100 by 20. So 5 ampere, not exactly 5 ampere, that we will put here 5 into e raised to power minus t by tau. Okay. So here it is flowing 5 in 1 minus e raised to power minus t by tau. And here we already computed IR is equal to 100 by 5k, right? So 20 milliampere. So IR is 20 milliampere. IL is 50 milliampere. So by ACL, IL should be 30 milliampere.
70.
Oh, yeah, correct. Sorry. So no, uh, 30 only, right? 30, right? Let me clarify this. Okay.
Yes, sir. 30.
Now, I latch would be equal to IR plus IL, right? I latch is 50 milliampere. IR is 20 milliampere. IL we have to find. So IL will be 50 minus 20, so 30 milliampere. And now we have an expression of IL, that is 5 into 1 minus e raised to power minus t by tau, and tau is nothing but L by R, and L is 0.5 Henry and R is 20 ohm. 0.5 by 20, so it is 40, 1 by 40, so 30 milliampere. 30 into 10 is power minus 3 is equal to 5, 1 minus e raised to power minus 40t, right? Because tau is 1 by 40, so 40 will go on numerator, and this is your expression, right? So now you have to apply the log thing here. If you divide it first, 5, 6, so 1 minus e raised to power minus 40t is equal to 6 into 10 raised to power minus 3. If you take ln on both sides, you will get an expression, right? And that expression would be, let me write it, minus 42. What value you will get? If you take ln into e, it will be straight away 40t, and ln1 would be 0. So 40t and ln of 6 into 10 to the power minus 3, that would come out to be minus
Minus
6
5.11.
of ln 6 to the power 6 into 10 to the power minus 3.
It's minus 5.
Okay, let me write it what I have already calculated. If it is wrong, you just update it. So finally, you will get t is equal to 1.5 into 10 raised to power minus 4 second. Is it matching with your answer? This is the answer here. This much of pulse width you need to provide. Just verify at your end. Okay. I hope this
Yes,
is
sir.
correct. Okay,
I'm
thanks.
getting the same.
Thanks. So I hope you can solve now any kind of question based on the latching current, right? Because we discussed two problems based on that. Let me see any other concept we should discuss. Or if you have anything in your mind, you go ahead and we can discuss that. Okay, so okay, so uh, 10 more minutes are here, so we will just one problem from last assignment, and just to clarify any doubt of the losses. This was given in assignment 2. So anyone who get wrong answer for this question, this one,
So for this question, if we consider this ICEO,
ICEO you have to consider. Yeah, here because here it is given. So you have to consider ICEO for off state, and off time also you can easily find out from
the subtracting,
mitigating the rise time, fall time, and on time from total time. And total time is nothing but 1 by 10 kilohertz. So 100 microseconds.
Sir, the assignment solution will be published in the portal, right?
Yeah, I hope that will be published soon.
Okay.
I hope. So okay. So you everyone got correct answer, or did anyone fail to get correct answer? Anyway, so let me go ahead and discuss it with last 10 minutes. And if anyone is, or if no one had any issue in that, or if someone has not issue in that, you can leave the session because this is last 10 minutes and I am going to discuss this question. If you want to see the solution, you can stay, otherwise you can. So I will move step by step. Conduction, switching on. Okay, I will apply that shortcut that I told in the beginning of the session. So if you want to see that, be there, please. So P conduction is straightforward. That is DC sat into IC. So zero point 0.2 volt is given in the problem. 0.2 volt into 5 ampere. So that would be 1 watt. So see, this 1 watt is your conduction loss and it will be the dominated loss. Okay? And I told about switching losses. If these kind of curves are there, triangular, one is falling and one is rising, then you can apply straight away VCE here, the peak value of VCE and the peak value of IC. Okay. Let me write it down. Peak value plus IC peak by 6 into D, right? So that we will take for on also and off loss also. So VC peak was that VCC is given when it is VC peak, when it will be peak when the switch is off. So all the voltage across VCC that will come down to VCE since no drop will occur across this collector resistance. So VCE peak will be equal to VCC, which is given in the problem, that is 9 volt. So we will take that as a 9 and IC peak will be the value when this switch will conduct, right? So that is 5 ampere given in the problem. So that we will take 5. Okay. Yeah. So here from this calculation we will get 9 5 is 45 by 6. Now we are taking both losses at once, turn on and turn off. So this rise time and fall time divided by time, total time period, that will be your duty ratio, right? And since it is given in terms of frequency, so we can write it further 45 by 6 into TR plus TF into switching frequency, right? At once we are computing both the values and rise time is given, that is 5 microsecond and fall time is 10 microseconds. So for our electricity 5 microsecond and it is 10 microsecond and frequency is given 10 kilohertz. So 10 kilohertz.
Sir, for conduction loss also we have to consider T on and F, right?
Oh, yeah. You are correct. I forgot that. Yeah, this is a really silly mistake that we need to include here. That T on time is 50 microsecond. Yeah, here D on. Let me include that. Thanks for reminding it. D on, and that will be 50 microsecond and into frequency. That frequency is 10 kilohertz. So 10 raised to power 4 and
Point
50
five.
0.5 watt. Yeah, correct. Now I recall the value. And here,
Sir, for peak conduction,
mhm,
we are taking it as VCE into ID. Sorry, IC.
yes. VC into IC we are considering, and for how much time it is conducting,
Okay.
because power is a function of time. For how much time you are conducting it, that much losses will be there.
Okay,
So for
sir.
that purpose, we considered on time duty ratio. And here for switching losses, we now at final step where we have to just compute 45 by 6 into 15 microsecond. This is turn off and this is turn on. So both switching losses into 10 raised to power 4 and that will come out to be mm, 3 2 just 6, 5225 by 2 into 10 to the power minus 2, so 112.5. So I think it will be 1.125 watt. Am I correct? 1.125 watt will be total switching loss. And off state loss, during off, the value of VCE into ICEO. What you were saying, that some current will flow due to majority carrier devices, that will be your leakage current. So when this current is emitted to collector when base open, so that is VCE we have anyway, that is for off state, that VCE is equal to, where was it? Yeah, 9 volt. So 9 volt into VCE is
IC is
IC,
100 microampere.
ICU is 100 microampere. That will be
0.9
milliwatt, right? 0.9 milliwatt.
milliwatt.
So all are in watt and it is in milliwatt. So if we add all the loss,
This is not there in case of MOSFET, no? P off.
yes, it will not create any
Just
difference.
if this P off is not there.
Yeah. So 1.125 plus zero point 0.5 plus 0.0009, I guess. 1.6259 will be there, right? So it is your total losses, and your answers is in the range of 1.5 to 1.9. So it will perfectly fall in the range, and this will be your answer. So even if you would have forgot to include this loss, your answer would have been fallen in that range. But it was just there to give you idea that how much significant this kind of loss. So I hope this session should be useful to you. Uh, it is the time to conclude the session. If there any final doubt, I am happy to take. Otherwise, we will conclude the session. Okay, then thank you everyone. Thank you so
Sir,
much.
the
Yeah, go ahead, please.
sir, the PDF of last session need to be changed. Just reminding you.
Okay, so PDF you are saying, right?
Yes, sir. PDF once we have downloaded to our system, it is not viewable.
Definitely, I will modify that and I will verify once before uploaded, and I will upload both sessions PDF. Thanks for
Sir,
reminding. Yeah, Santi, go ahead.
sir, this fifth question, sir, this assignment, this transistor assignment, fifth question, the choose for NPN transistor, which one is true?
Uh, First question of week 2 or week 3? Sorry, which question? First
Fifth
question of
one.
fifth.
Fine. Fifth
Fine.
one, sir.
Okay. Fifth question of current assignment or assignment 2?
True, sir.
2. Okay.
Yes, I didn't understand that option one, sir, false given. Second option, saturation VCE is greater than VBE, that is wrong, that is accepted. Collector to emitter leakage current flows only when BJT is on.
Yeah. This one you did not understand?
Yes, sir. That
Okay, fine. So
So the collector to emitter leakage current flows when BJT is on. That
Ah,
T not flows even when it is in
yeah, so that
when there is
collected,
no current.
yeah, collected to emitter leakage current flows only when BJT is off, right? That
Yes,
where,
that is due to temperature. The minority carriers can flow.
yes, yes, yes.
Temperature effect. So
Yeah,
that
yeah.
one is okay. First option, sir.
Uh-huh. First option, base driver source should have sinking capability so that negative base current can flow. So in this you have some trouble, right? Okay. So see, generally all the drivers to operate any power electronics circuits or converters, we design some gate drivers, right? Gate drivers for our MOSFETs or base driver for transistor, this BJTs. So uh, when you turn off, uh, we saw in the lectures also, we need to apply some negative base current. Let me bring back that curve. Just give me a moment.
Sir,
Yeah, yeah. Please go ahead.
sir, can you explain fourth question, sir, in assignment two?
Assignment two, fourth problem. Okay, just a minute. I will definitely explain that problem. Just let me complete this one. Uh, okay, so actually, unfortunately, I'm not able to find that curve. So I will tell you what happens. So uh, when you try to turn off, you apply some negative base current for that delay time, that turn off delay time, I guess. And during that time, your
Storage time and off time.
yeah, 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 a storage time and off time. So during that time, we apply negative base current. So our thyristor, sorry, our this BJT should have the capability to carry that much of current. What it is uh, written here, base driver source should have the sinking capability so that negative base current can flow. So it should have that much capability so that it store back those charges which are getting stored during off period. So that's what this statement means. This first statement means it should have that much of capability so that it can store those charges which are created by negative base current.
Okay. Which means that it can able to withstand that much negative voltage.
Yes,
Base.
if you apply negative voltage at base, right? Yeah. So another question was question 4. So let me take question 4.
If in the same problem we consider, it is said that BJT is an unipolar voltage
Yeah,
device.
BJT is a unipolar voltage blocking device, right? And
What do you mean by that, sir?
okay, in the same question, yeah. So see, BJT has a certain. Let me draw a BJT. So it basically blocks this. it will start to flow after VC is sat, right? VC sat.
That
So
I see.
it is able to block that much region. So and that too is positive voltage. So that's why it is called as positive voltage blocking capability it has. And similarly, if you see thyristor, so thyristor has also a positive blocking capability as well as negative blocking capability. So maybe next session we can discuss more on blocking capability or like polarity of blocking how it differs from device to device. So for
Okay.
BJT, did you get that? It is blocking this much. That's why it is called as
Unipolar voltage, we should consider that voltage blocking capability. The meaning is
yeah.
that voltage blocking capability.
Yes, yes.
Oh,
Yeah.
it blocks unipolar. It blocks positive voltage.
It blocks positive voltage. Yeah, like diode. Let's take example for diode. Very simple example. If you apply positive voltage, it will conduct. If you apply negative voltage, it will
It
block.
will not block.
Yeah, it will block. So that's the meaning of blocking.
Okay, so it means that BJT blocks till VC equal to VC is that.
Yes, yes, yes. Even if it is blocking for a very small period, then it can be considered as it is blocking that polarity. It may conduct after even a diode also it may break down in negative region, right?
Yes, sir.
So that we do not consider, but even if it is blocking for a small period in conduction direction, so it will considered as a positive blocking. Or if it is not at all conducting in that negative region at a starting, it will be considered as blocking in negative. So diode will be negative voltage blocking.
It blocks it. Here here also we can say it blocks negative voltage.
This IGBT, no,
Yes, BJT.
BJT, yeah. See, some leakage current will flow in BJT, you know.
Yes, sir. That is reverse bias of
Yeah. So that,
base collector junction.
though that is a small current, but there will be that.
Okay.
Okay.
Thank you, sir. Thank you.
Yeah. Thank you. So let me come back to question number 4. I think someone has asked. So, uh, see, we need to identify the maximum value of RB. This RB. At certain point of time, I think at final steps, you need to put some value of beta, either 10 or 50, so that our limit can be decided. That we will go step by step. So first we will apply 2 KVLs. In 1 KVL at outer loop, 1 KVL at inner loop. Okay. And since all the saturated value is given, so we will consider it as a saturation since it is acting as a switch. Now, here IB is not given, okay, and here IC is also, I guess, not given. And let me mark out the terminals. VC, VE, right, and VB. Okay, VB is given 10 volt. Oh, sorry, VB is already given here. So let me denote it with a smaller VB. Okay, it is confusing. Okay, so this 10 volt is given here. Uh, RB is not given, I guess. RC is given.
RB, we
So
have to find the range.
Yeah, of course, RB we have to find. So first we somehow find IC, okay? Then we will be able to find IB, and further we can find out that resistance, and then we will apply that IC is equal to beta IB, but IC should be less than beta IB for the saturation region, and it should be less than minimum that value that we have to find, right? So if we solve it, it would be more clear, right? So VCC is your 100.5 volt, and VC is sat is given VC sat is given zero point 0.5 volt, so it will be 0.5 volt. So IC you can compute 100.5 minus 0.5 divided by RC, that is 25, and IC you will get 4 ampere. Okay, and to operate it as a switch, it must be less than beta IB. Okay, so and beta, the range of beta is given, okay, from 10 to 50. So let me write it further. IB should be greater than 4 by beta. Okay, this is another way of writing this relation, right? If IB is greater than 4 by beta with the beta value of 10, right? Uh, if we consider the least value of beta, take two cases, beta is equal to 10 and beta is equal to 50. So case 1, if IB is greater than 4 by 10, that is zero point 0.4 ampere, then it is guaranteed that it will be higher than 10 by 50. Sorry, 4 by 50 if we take beta is equal to 50. So IB must be greater than the higher value, right? Because once it is valid for one condition, then it will be true for another condition. So once IB is greater than zero point 0.4, then IB will be definitely greater than 4 by 50. That will be 0.08. So we will take the value of IB, that will be 0.4, right? And that's what we just needed to identify. After that, it is a really a straightforward problem. We need to apply KVL in at inner loop or input loop, and that will be IB is equal to 10 volt, that is VB, minus VB is at that is given 0.8, divided by RB, right? So further we can simplify it as RB, we just need to find RB. IB anyway we have computed by the condition which is given in the problem, and it will be your 9.2 divided by IB. How much we computed? That is 0.4. It should be minimum 0.4 so that your maximum value of resistance you will get, right? So minimum it should be 0.4,
23.
and that you will get around 21,
23. 23.
23. Thanks. 23 ohm. That you will be. That should be in the range, I guess. Hmm. Yeah. So 23.1 till 23.1 you could have achieved. So 23 ohm is the answer. Any doubt in this? Anyone? Okay. So I hope it is all.
When we substitute this IB for 0.008, RB will be maximum.
Yeah, because for saturation, if you consider
So
0.008, that
IB
will
should be
be
greater.
IB should be greater than minimum zero point 0.4. Just if one number is greater than 4, one number is greater than 8, so by two conditions you just need to conclude the conclusion. So that's it. Any other question or any other doubt? Or should we conclude here? Anything in chat box? Can you please give video link? I think you all guys must have been shared with a link or sheet. One Excel sheet is there where all the lecture notes and videos will be provided. So if you do not have that, I will share that in the chat box. Okay. Okay. So I am pasting the link in the chat box. You go to the link and yeah. So with this spreadsheet, you will have access to all the live sessions related to this course and all the lecture notes related to this course. You can access that. So from next session, we will go ahead with rectifier, I guess. Right? Week 4 module is rectifier. So okay, so I will see you next week, same day, same time. Thank you very much. Thanks a lot to join.
Thank you, sir. Thank you so much.
Thank you.
Thank you, sir.
Thank you.